All right, so we're going to be solving for the amount of energy that if you have a spring and compress it, how much of that spring's compressed potential energy goes into kinetic energy of two arbitrary masses attached to it. So we've got some rest length L, some spring constant K. I'm going to measure the displacement of the second mass as x2 inward like that, and this displacement as x1 measured like that, relative to these rest length positions, right? So delta x, this is like the compression of the spring, is just x1 plus x2 for any position you can put these masses in, like that. So we have that. Hooke's law says F equals minus spring constant times delta x, and that's the force. That's the force on each of these, actually. It's not a matter of a negative sign because I'm measuring both of them inward, so the force is both negative on each, which is both like that, this on the left mass and that on the right mass. Okay, so this is a system of differential equations coupled with these positions. We can write that then in linear algebra notation, if you'll let me. We'll say we have a mass matrix multiplied by the acceleration of each of the masses. So this is F1 and F2 equals minus a K matrix, which is just so now 1, 1, 1, 1 times all the spring constant. And then this is a position. Each of the masses positions, displacements inward. Okay, so let's assume a solution that it's going to wiggle, right? That there's going to be some sines and cosines involved. So we're going to assume a solution of the form z of t equals some arbitrary constant times sines and cosines. Then z second derivative of t for this, because z of t is this solution, z double dot, will be nothing more than bringing down a minus omega squared to those, and then the exponential. So now we have the same mass matrix times this same mass matrix, right, times this solution form, and then the exponential, and then that side equals minus k times 1 times the exponential as well. Exponentials cancel, and now we can go ahead and add over this side to this side times minus omega squared plus k equals 0. Now we can factor out a. We've got now like that. And this looks kind of like an eigenvalue equation because we've got some matrix sum acting on a vector equals 0. The only way that can happen either way, though, is if this matrix sum has a determinant of 0. So let's actually write that out, and this matrix will look like then k minus m1 omega squared, and a k here, and a k here, and a k minus m2 omega squared. And the determinant of that will equal 0. So the determinant of this, we just FOIL these, and we subtract off the product of those. So we have k squared minus k m2 omega squared minus k m1 omega squared plus m1 m2 omega to the fourth minus k squared equals 0, and our k's cancel. Now I'm going to substitute in, I'm going to say chi equals omega squared to reduce the order of this, and we can solve it like a quadratic. So m1, I'm just now rewriting this with chi. m1, m2 times chi squared minus, this will factor to be minus k omega squared, which is chi, times m1 plus m2 equals 0. Quadratic equation will say that chi equals minus k, this, so that's plus k m1 plus m2 plus or minus the square root of b squared minus 4ac. C is 0, so there's minus nothing. And that's k squared m1 plus m2 squared. This is all over 2a, 2m1, m2. Okay, so if so this here, k squared plus m1 plus m2 squared, or k squared times m1 plus m2 squared, that's just, since the square root is just k times m1 plus m2, which is the same thing here, so when you subtract it, you get 0. So chi equals 0, or when you add it, you get 2k m1 plus m2 over 2 m1 m2, and the 2's cancel. So that's chi, and that equals omega squared, right? So we won't worry about square rooting that, unless we need to. Maybe we don't. So, what is omega though? Omega is the period of oscillation of either the masses, and it's also the period of the frequency of oscillation of delta x, basically, of the actual spring's compression length. So knowing that, let's look at delta x over time. It's going to start at some maximum compression, and then it's going to go down and up like a cosine, right? So we're interested at this point here, at which point it's reached maximum velocity, and it's going to start to slow down after that point. But we don't care about after that point, because at that point the masses will have already flown away. They're already going to be leaving the spring because the spring will be slowing down. So it will not be doing anything to the masses after that. So this is 1/4 of a period, and that's all we care about. So now we want to integrate Hooke's law, the force over time, for this amount of time. 0 to t over 4 for Hooke's law minus k times this compression times cosine of omega t, like I was saying. Okay, so we do this integration, we get delta p equals minus k c times sine over omega of omega t evaluated from 0 to quarter period. So what is a quarter period then? In terms of omega, a quarter period is, so 2 pi frequency equals omega. F equals omega over 2 pi. The period equals 2 pi over omega. So a quarter period equals pi over 2 omega. That's what we're putting into here. So our change in momentum equals now minus kc times sine of pi over 2 omega times omega, and the omegas cancel, and the whole thing's over omega. So it's just sine of half pi, which is just 1. And so because of that, our change in momentum is now just minus kc over omega. And that's for each block. It's negative because as just the way they were measured. So really, that's a little bit arbitrary. Now, these I will leave up here, and we're going to find the energy. So the energy, kinetic energy, will be, for any given thing, its momentum squared, if you know it, divided by twice its mass. Okay, so let's find the kinetic energy for mass number 1, the one on the left of the spring. So KE1 is going to be this squared, K squared C squared, divided by, sorry. Okay, so as I was, let me rewrite this. We have K squared C squared over omega squared, all from squaring this, divided by 2m1. Okay, so omega squared we have right here. That's the point. So we have omega squared. We could put that in. We say KE1 now equals K squared C squared over K m1 plus m2. That divided by m1 times m2. And that whole thing divided by 2m1. So it's getting a little messy, but it's nothing too bad. So we lose our K there. And from this part here, we can lose an M1. Okay? Well, that's fine. So anyway, this simplifies. We have K C squared over M1 plus M2. The M2 comes up, and the 2 stays below. So Ke for the first mass is 1/2 K C squared times M2 over M1 plus M2, right? And this right here, this 1/2 K C squared is nothing more than the 1/2 K delta X squared potential energy of a spring being compressed. So the amount of kinetic energy that the mass gets is the amount of potential energy that the spring had to give times the other mass relative to the total mass. So then the more massive, from the first diagram here, the more massive this is, the more kinetic energy goes into this, and vice versa. The smaller this is, the less goes into this. And that's pretty intuitive, but I like that it comes out basically exactly as you could intuit for it. And then Ke2 will just be going through the same algebraic process, M1 on top over the total mass. And that's that. So